Bismillahirrahmanirrahim. Assalamu alaikum dear students. I hope you all are fine and in the best conditions of your health. So in continuation with the online lectures for the course of Fundamentals of Organic Chemistry, today we shall discuss about the resonance, and before going into detail about resonance, we shall discuss firstly about the concept of formal charge, and also we will see about some minor details about the delocalized bonding. Right, so in this lecture the basic concepts which we will study is the resonance structures, formal charge, localized and delocalized bonding. So firstly we'll consider about this resonance. So what's resonance? Resonance in organic chemistry, when we are considering, it means it's just theoretical concept, right? Resonance is nothing, but when you are considering the resonance in organic chemistry, it's a theoretical concept, right? It's just a paperwork. And when resonance is involved, the resonance comes into action when a molecule is conjugated, right? And what we mean by conjugated is any system that has alternate single and multiple bonds. So if they're double bond and the next is a single bond, then double bond, then single bond, right? This is known as alteration. So if there is alternate single multiple bond, single double bond, or single triple bond, right, in that case the system is said to be conjugated. And whenever the system is conjugated, we cannot draw a single structure to explain the conjugated system structure, right? Just for example, let's take a simple example of this. So suppose we have the structure, and we'll see about what we mean by resonance, or what we mean by this conjugated system, right? So in this system which we are considering here, this is butadiene, right? So it has 4 carbons, so it's a butane system, and since there are 2 double bonds, it means it's a diene, right? And the position of double bond is such that 1 carbon and second, right? So there's a double bond between first and second carbon, so we'll consider as carbon number 1 has a double bond, and similarly this is a 3rd carbon and this is a 4th carbon, so there's a double bond between carbon 1, 2 and carbon number 3 and 4, right? So this is known as 1,4-butadiene. So if you see the structure, it means that there's a double bond between 1, 2, and there's a double bond between 3 and 4, but there is a single bond between 2 and 3. Simple, it's a structure explaining everything, but there is something missing. When we carry out the experimental calculations of the bond length, it appears that no, so the double bond is not only between 1, 2 and 3, 4, so there's also a double bond between 2 and 3 as well. Why? Because this bond length for double bond and this bond length for double bond, right, they are justifiable in the double bond length, but this single bond has a bond length which is also equal to these bond lengths. So what this means, it means that if the bond length of this double bond is equal to the double bond, the bond length of this, it means there should also be a double bond, right? So but if we draw a double bond right here, then what happens that we are creating a problem with the valency rules. So in that specific situation, this carbon will have 5 bonds, similarly this carbon will have 5 bonds, right? So we cannot draw this structure, and if we do not draw this structure, if we draw only this structure, then in that case we cannot justify the bond length of this central carbon, right? So what we do, we say that instead of drawing this simple structure to explain the structure of butadiene, we make use of 2 structures. So in the first structure we have the double bonds between carbon 1, 2 and carbon 3, 4, and in another structure we say that there is also a double bond between carbon 2 and carbon number 3. And when we are showing this double bond, so we are not showing double bonds here, right? So that's the purpose, and we say that actually both of these are not the actual resonance structures. Both of these are not the actual real structures, but actually both of these are useful to explain the structure of actual butadiene, and that actual butadiene cannot represent it here, because if we represented that structure of actual butadiene here, then we would have violated the rules of valency, right? So when we make use of two or more structures to explain the structure of a real object which cannot be drawn otherwise, then this is known as resonance, right? And the structures we make use for explaining that real structure, those structures are known as the canonical forms, right? The structures are known as canonical forms, or they are also known as the contributing structures, right? Or they are simply also known as the resonance structures, right? So these structures, so it means that in specific case, this structure, this butadiene and this structure, both of these are not the actual structure, but they are actually known as the resonance structures, and we may also call them as the canonical forms. We may also call them as contributing structures, right? And since both of these structures are not real, so we make use of arrow like that, right? So this arrow is known as the resonance arrow, and whenever you see this arrow, it means that the two structures at the both end of this arrow, they are contributing structures, or they are resonance structures, and they are not real, right? So whenever you are describing something which is contributing structure, which is not real, then we make use of this resonance structure, right? So next we will move on to our concept of this formal charge. Right, so just hold on. So we'll see about what we mean by a formal charge, right? So consider that we have a positive ion or a negative ion. So we are sure that this atom has a positive charge or this atom has a negative charge. For example, take the example of sodium ion, right? So we know that this positive charge is on sodium. Similarly, if we have a chloride ion, we know that its negative charge is on chlorine. But suppose that if an ion is polyatomic, means that if an ion consists of more than one atoms, then we might ask that which of these atoms has the charge on it, right? For example, you may write CrO3, so you may be curious that this negative charge is on which atom, right? So it's important to know about the charge distribution, and it's important to know that which atom is electronically rich or which atom is electronically deficient, because the atom which is electronically rich, it is basically the nucleophile in organic chemistry, and the atom or group of atoms which are electronically poor or electronically deficient, they act as the electrophile in the organic chemistry, right? So when we have to interpret the organic chemistry, or when we have to explain the reaction mechanism, it becomes important about which center, which atom or which group of atom is electronically rich and which is electronically deficient, right? So this concept of electronic distribution is very important in order to interpret many facts of organic chemistry, including how and why reactions occur. So this study of how and why reactions occur, this study is known as the mechanism. Second, how molecules interact with each other, right? So which is the deficient and which is rich, and what are the physical interactions or attractions between different molecules. So these attractions or interactions are all dependent on electronic charge distribution, right? So it becomes important for us to know that which of these atoms has actually the higher electronic density, or among a polyatomic ion, which of the atom is actually the bearer of charge, which atom carries the charge, right? So from quantum mechanics, we know today that the electrons are shared between neighboring atoms, or they can even be shared by the whole molecule, right? Secondly, because atoms differ in their electronegativity and also differ in their hybridization, we cannot assume that electrons are shared equally, right? So whenever you have two different atoms, whatever be the electronegativity difference between them, right? So electrons are not shared equally. For example, we may call the carbon-hydrogen bond almost non-polar, but still there is some polarity because this carbon is slightly more electronegative than hydrogen, right? So as a result, we say that this carbon atom, which is attached to hydrogen, that has slightly higher electron density as compared to hydrogen, right? So according to quantum mechanics, unless the bonds are between the same atoms, otherwise the electrons are never shared equally. So electrons are only shared equally when there is a pure covalent bond, right? And a pure covalent bond exists only between two identical atoms. A pure covalent bond exists only when the bond is between two same atoms. For example, if the bond is between chlorine and chlorine, so both of these are identical atoms, this is 100% covalent bond, and in that case the electrons are shared equally, right? Otherwise, if the atoms are different, then electrons are never shared equally. And because of this unequal sharing, the atoms have some fractional charge, right? So this charge is fractional, it's not integer. So what do you mean by integer? Integer means a full whole number. So 1 is an integer and 1.5 is a fraction. Similarly, 2/3 is a fraction, right? So because of this unequal sharing, the atoms have fractional charge. So they don't have integral charges. So integral charges always appear when there's an ionic bond, right? So when you have a sodium with a positive charge, so it has +1 charge. But in case when you are saying about the covalent bond, we cannot show the integral charges, right? Because there's no full charge existing. So we only show the fractional charges, right? And there are calculations which help to determine the exact electronic distribution and atomic charges, right? However, these calculations require complex computational programs, and in order to run one program, it often requires a number of hours. It's a very time-taking process, right? So just to summarize further, for what we have learned is that if there is a pure ion, then there is no problem. We know for certainty where is the negative charge or where is the positive charge. But when in case if you are considering polyatomic ion, then you have to consider that which atom is exactly bearing the charge, or where is the electronic density that's maximum, where is the electronic density that's minimum. And why the electronic density is important for us, because on the basis of this electronic density we decide if the atom is electronically deficient or if it's electronically rich. And why we are interested to know the electron is electronically rich or deficient is the reason is because that on this basis we have to decide that which atom will be nucleophile, which atom will be electrophile, and these information are important for us to help determine the mechanism, and the electronic distribution also help us define the chemical properties and the physical properties of the molecule which are studying. Further, we have seen that the quantum mechanics shows that electrons are never shared equally, and the atoms which are bonded through a covalent bond, they have a fractional charge. So we cannot show an integer charge because we are here considering about the covalent bond, right? And in order to calculate this fractional charge, so there are complex computer programs which are very complicated, and also they are very much time consuming. So we as a chemist, we need to know rapid estimate. We just don't want to know about the exact fractional charge that existing on the atom. We just want to know that which is rich and which is deficient, right? So in order to just estimate the charge distribution, okay, we just want to know the rough estimate, right? So that we can just decide that which is rich and which is deficient. So there is a very simple method to determine, right? So if there's a molecule, there's a covalent bond, and if we have to decide that within this molecule, this atom is either neutral, or it has a positive charge, or it has a negative charge, right? Just imagine, just consider, and just remember that here we are talking about the covalent bond. We are not talking about the ionic bond, right? So if there's a molecule, and if you have to determine that within this molecule, if a certain atom is neutral, or it has a positive charge, or there's a negative charge, right, then we can determine the charges. However, this method we are using for the rough estimate, this method has a limitation that it provides integral charges only. Means that will give us charges in whole number, right? So I already mentioned that in order to determine the fractional charges in a molecule, that we have to make use of computational programs. But since we are to need the rough estimate, so we will take the rough estimate and the answer will get in the form of integral charges. But just remember that this is just the estimate, right? So integral charges only appear in case of ions, but since we are taking the rough estimate, so we cannot calculate the exact fractional values by this method. What we'll get the integral charges. We will get full whole number, right? So this method provides some indication of charge distribution, and by this method we can find the electronic distribution within a molecule or ion, right? So these charges, or these integral charges, which we will determine in a molecule, these integral charges are known as the formal charges, right? And that's the topic for our discussion, right? So what we do, we take a molecule, or we could take an ion, and we will make some calculations, we will make some simple calculations, and we'll get some integral charges. So these integral charges, if the charge is 0, it means that atom in a molecule or that atom in an ion is neutral. So if we get a positive integral charge, then it means that that atom is deficient. And if we get a negative value, that means that atom in a molecule or that atom in an ion will be electronically rich, right? So these integral charges which we will get, these integral charges will be known as formal charges. So if we have to define a formal charge, right? So what's a formal charge? Formal charge is a comparison of electrons owned by an atom in a Lewis structure versus the number of electrons possessed by the same atom in its free state. For example, suppose we have an oxygen atom, right? And the number of electrons owned by oxygen atom in the free state, and then we have this oxygen atom, and it's in a combined state right now. It's in the form of a molecule, right? And since it's in the form of a molecule, you can draw the Lewis structure, right? So suppose consider this example. Suppose we have an oxygen, so we know that the oxygen has 6 electrons in the outermost shell, right? So the number of electrons of this oxygen atom in the free state are 6. However, when it's in the combined state, or when it's in the Lewis structure, you can just count, just ignore this whole fragment, just consider this oxygen atom, right? So the number of electrons around this oxygen atom, if you can see, how can you count them? So these are 8 electrons, right? So this is formal charge. So it's just a comparison of number of electrons owned by an atom in Lewis structure. So this is a Lewis structure, and we have to compare the number of electrons owned by this atom in Lewis structure, and we have to compare it with the number of electrons that's possessed by the same atom in its free state. Right, the number of electrons possessed by this oxygen in free state is 6. However, the number of electrons possessed by this atom in a Lewis structure, in this particular Lewis structure, there are 8. Right, so this comparison is known as a formal charge. Right, so in this structure we have, in this definition, we have made the use of the term known as Lewis structure. So you may be curious to know what we mean by Lewis structure, because often we come across this term of Lewis structure. What is Lewis structure? Right? So Lewis structure, also known as the Lewis dot diagrams, or Lewis dot formula, Lewis dot structure, electron dot structure, Lewis electron dot structures, and some people simply write it as LEDS. So these Lewis electrons or Lewis structures, they are diagrams that show the bonding between atoms of a molecule, right? And they also show the presence of electrons if they exist between the molecules. Just see the structures. So we have nitrogen. Here you can say that there are 2 electrons between nitrogen and oxygen. It means these 2 electrons are shared between oxygen and nitrogen. Here you can see there are 4 electrons. It means they are 2 electron pairs. So nitrogen is forming a bond with oxygen and nitrogen is forming another bond with oxygen. So there is a double bond between oxygen and nitrogen. You may also see that there is 1 electron on nitrogen. What does that mean? So there is an unpaired electron on nitrogen here. Similarly, if you see here, then this oxygen, you can count the electrons. This oxygen has 6 electrons. Just see, the number of electrons possessed by this oxygen and this oxygen are different, although both are oxygens. So this comparison of number of electrons by an atom in bound state and the comparison of the number of electrons which are possessed by the same atom in free state, this comparison is known as formal charge. And the diagrams in which we show the electrons as dots, and it shows the presence of bonding electron as well as the presence of lone pairs. Such structures are known as the Lewis structure. So next we'll consider that what's the process for calculating the formal charge and how can we determine if the molecule we are considering is electronically deficient, or the certain atom is electronically deficient, or the certain atom is electronically rich. So this procedure consists of 3 steps. And before starting the steps, let's consider that we are taking the example of a simple molecule of hydronium ion here, right? So this is hydronium ion, so H3O positive, and you might have seen this structure, seen this ion very frequently in different organic reaction mechanism and biochemical reaction mechanism as well, right? So let's move to step 1. The first step when you are to determine the formal charge involves drawing the Lewis structure. And when you are drawing the Lewis structure, right, you have to include all unpaired electrons as well, right? You don't have to hide anything. So you have to show the bonding electrons, you have to show the unbonding electrons, right? So never forget to involve the unbonding or the lone pairs of electrons, right? So under these conditions, this is the structure for hydronium ion. So you can say this oxygen is forming a covalent bond with the hydrogen, so there are 2 electrons present between hydrogen and oxygen. Similarly, there are 2 electrons between this hydrogen and oxygen, and there are also 2 electrons between this oxygen and hydrogen, right? So here we are showing this square bracket that indicates that positive charge belongs to the entire molecule, right? And we have to determine now that where is this positive charge residing. So either this positive charge is on any of these hydrogen atoms, or this positive charge is on oxygen atom, right? So in order to determine the formal charge, here we have to use the formula. So formal charge, which we are representing here as Fc, that's equal to the group number of an atom, right? So group number means the group number in the periodic table minus number of lone pairs or number of unpaired electrons present here, right? Unshared pair of electrons present here, so that means the lone pair. And then we have the bonding electron pairs, so number of electrons shared in a covalent bond, and we have to divide by 2. For example, if there is an oxygen hydrogen single bond, the number of electrons shared will be 2, and we have to divide it by half, right? So that will become 1. Right, so this is formula for calculation of formal charge. So to do the atom for which we are calculating the formal charge, we have to consider that's group number minus the number of lone pairs or number of unshared electron pairs it has, minus half the number of electrons shared in a covalent bond, right? So now we have formula, and now let's see that how can we calculate the formal charge for this hydronium ion. Right, so firstly we'll calculate the formal charge for hydrogen, right? So we know that it has 1 valence electron since it has a group number 1, right? So G will be 1, and now there's no number of unshared electrons, right? So minus 0, and there are 2 electrons in the oxygen and hydrogen covalent bond, so we have to take the half of that, right? So 1, the group number, minus this number of unshared electrons, minus 0 minus the half of 2, that's 1, minus 1. So that will become, the formal charge will be equal to, right, so we can write the formal charge in that specific case will be, right, so formal charge for hydrogen will be equal to 1, that's a group number, minus, since the number of unshared electrons or the number of lone pairs is 0, minus 0 minus, so there are 2 number of shared electrons, right, so since we have to take the halves, that becomes 1, right, so 1 minus 0 minus 1, that equals 0. It means that the hydrogens have 0 formal charge. What does it mean? It means that in this molecule the hydrogens are neutral, right? So if you say, in case you have to take a hint, if you see a molecule, right, and if you want to see that if hydrogen has a formal charge or not, just remember that whenever hydrogen has only one covalent bond, right, if hydrogen has one covalent bond, then its formal charge will always be equal to 0. What does that mean? That hydrogen will be neutral in this molecule. So one thing is important, that hydronium ion, all of the 3 hydrogens don't have any positive charge, right? So let's see what's the case in case of oxygen, right? So let's calculate the formal charge for that as well. So what we do is write the formula. So in case of formal charge for oxygen, we know that the group number for oxygen is 6 minus, so oxygen is member group number 6, so group number 6 have 2 electron pairs, 2 lone pairs, so minus 2. Then we saw that in hydronium ion, just I'm going for the back slide. So in case of the hydronium ion, so there were 3 covalent bonds of oxygen with hydrogen. Alright, just remember that in 3 covalent bonds, so each bond has 2 electrons. The 3 bonds will have 6 electrons, right? And we have to take the half of 6. So that will become 3. Right? So the answer for that will be, just calculate 6 minus 2 minus 3, that becomes minus 5. So 6 minus 5 becomes 1. The answer is positive 1, right? So it means, what does it mean? It means that this oxygen and the hydronium ion, actually it has all of the positive charge on it, right? So there's no charge on hydrogen, so there's only charge on oxygen. So by means of this calculation, if you subject this calculation to any organic molecule or any polyatomic ion, we can decide by this simple calculation if the atom, if a certain atom in this molecule has a positive charge or it has a negative charge, right? Whatever be the circumstance, we can calculate that by means of formal charge, right? So the third step, when you have calculated all the formal charges, is that sum all of the formal charges, and that all of the sum must always be equal to the overall charge on that molecule. For example, in case of hydronium ion, we saw that hydronium ion has +1 charge. It means if we sum up all of the charges we have calculated, the sum should be equal to +1. So just remember that in case of hydronium ion, the hydrogens had 0 charge, right? So there were 3 hydrogens. We would say that we multiply this hydrogen with 0, plus there was 1 positive charge on the oxygen, so +1, right? So 0 plus 1, that becomes +1. It means our procedure is right, right? So in this way we can calculate the formal charge. Alright, so after you practice this procedure with fuse structure, you'll begin to notice that there's some pattern. By just seeing the molecule, instead of making the calculations, you can just see the structure and you can predict the formal charge. So we'll see some patterns that appear and which help us in determining the formal charge on a molecule. So pattern number 1, right? So whenever you have written a Best structure, Best-Lewis structure, or in case of resonance, you have considered the best resonance contributing structure, right? Then the best contributing structure, the contributing structure that has the highest contribution, will have the least number of atoms with formal charge, right? So if just you remember the rules of resonance, so what we say that the resonance structure which has least charge will be most stable. The same applies here, that when you have written the best Lewis structure and when you have written the resonance with the most contribution, then that structure will have least number of formal charges. Let's, for example, I draw a structure and say that this structure is the most stable for all resonance structures. But you'll have in mind that since this is the most stable resonance structure, that means that least number of atoms will have formal charge in it. The second important factor, the second important pattern you can know, that if the atoms are attached to the same atom, right, then similar atom will have same formal charge. For example, you have a methane molecule here, so all of these 4 atoms, all of these 4 hydrogens are attached to this carbon. It means that if the one of the hydrogen has a 0 charge, 0 formal charge, then all of these 4 hydrogens will have the same charge, that will be 0. Right? So we say these 4 hydrogens are equivalent, they are the same. Right? So all hydrogens, or all atoms that are bonded to the same atom have same formal charge. So you don't need to calculate formal charge for separate hydrogen atoms. Similarly, if you have like this molecule of ethane, so there are 2 carbons and there are 6 hydrogens. So all of these 6 hydrogens are same because their environment is same. So both of these are attached to carbon and both carbons are bonded to each other, right? So in that case we say that all of these 6 will have same formal charge and both carbons will have same formal charge as well, right? Because there is no different atoms involved. The third pattern you will see in organic chemistry, that we only get formal charges of +1, 0 or -1. Right? So for example, you will not observe the +2 charge or -2 charge or -3 charge or +3 charge in organic chemistry, right? So you can get higher charges in case of only metals. Right? So whenever you are making calculation and your answer is coming about +3 or +2 or something else, you have to recheck your calculations, because when you are considering with organic chemistry, we normally don't get the higher positive charges. So only answer you will get will be +1, 0 or -1. Whenever you get a +1 answer, it means that carbon or that atom which you are considering is electronically deficient. Right? It means that's an electrophile. And if you get a negative answer like -1, it means that atom has high electronic density. And if the answer is 0, it means that atom in this molecule is neutral. It is not electronically deficient or it's not electronically rich. Right? So vast majority of the organic molecules are made up of small set of atoms, right? So you can see that hydrogen can be bonded with the carbon, or it can be bonded with sulfur, it can be bonded with chlorine in an organic molecule. That has limitations, but just recognizing the patterns, so that will speed up your understanding of how charges influence the reaction, how properties of molecule influence the reactions by means of electronic density. Right? So just remember that whenever hydrogen is forming one bond, it means hydrogen will have 0 formal charge. However, if it's not forming a bond, it is positive charge on single atom, definitely formal charge is +1. And if hydrogen is not forming any bond with anyone and oxygen is having negative charge, that means that hydrogen has a negative formal charge. But in case if we have a complex molecule, that it becomes difficult, right? So you have to see the patterns, and once you see the patterns, you can define what sort of formal charge that a molecule has. So just for a generalization, let's have this in mind. Right, so we'll consider the element and we'll consider the formal charges it can have. Suppose hydrogen, so here we have H negative, this is known as hydride ion. So hydride ions have -1 formal charge. But if hydrogen is forming a single bond with anything, then its formal charge will be 0. And if hydrogen is the form of proton, right, that's not bonded to anything, but this proton is having a positive charge, then its formal charge will be +1. So here we have C negative, carbon anion. So in that specific case, the carbon anion has a -1 formal charge, right? And if we have a carbocation, so here you can see there is a positive charge on here. So carbon is having 6 electrons, so this is known as octet. Octet because it requires 2 electrons to complete the octet, right? So it has not completed the octet, therefore we are writing here as open arclet. So in case of carbocation, the formal charge will be +1. So similar are these examples, and if you can see the example, and if you carry out your own calculations, you can just complete the formal charges. You can just calculate the formal charges. So as for example, just we are here, and here's the quiz for you, right? So there are 4 different polyatomic ions, and here you have to calculate the formal charge for each of these. So you have to calculate the formal charge for that methoxide, this methyl carbocation, right, and tetrahydroborate, and we have an oxonium ion here, right? So 2 are positive and 2 are negative. So these charges are written on square brackets because we don't know which atom has a charge. So you have to tell that which of these atom has the positive charge or which of these will have the negative charge. So far we have briefly revised about the resonance, we have revised about the concept of resonance structure, and we have known about the formal charge, right? The formal charge is comparison of the number of electrons an atom has in a bound state as compared to the number of electrons an atom will have if it's in a free state. So now the next concept we'll consider in a bit more detail is the localized and delocalized bonding. So in the previous lecture we saw that localized bonding involves the electrons which are fixed between 2 atoms, and the delocalized electrons are the electrons that are not fixed between only 2 atoms, but they're part of more than 2 atoms, right? So this distinction between localized and delocalized bonding only exists when we describe the electron motion using Lewis bond theory, right? So when we are not describing the movement of electron, we are not considering the motion of electron, right? Then in that case the concept of delocalized or localized bonding cannot exist, right? So according to this Lewis bonding theory, the localized electrons are normal. That means they exhibit the normal behavior, they remain fixed between 1 atom, and the localized lone pair, right, the lone pair on an atom that remains close to only 1 atom, right? So for example, if there is an oxygen, the lone pair of oxygen will only be close to oxygen atom as well. It will not be shared, or it will not go to any other carbon, that will remain close to an atom. And similarly, the bond pairs travel between only 2 atoms between which they are bonded, right? So this is the Lewis bonding theory, right? So according to this theory, the electrons are localized. And what we mean by localized, it means that localized electrons exhibit the normal behavior. A localized lone pair will remain close to only 1 atom, and the localized bond pair, means the pair of electrons that are bonded, will only move between the 2 atoms which with they are bonding. However, when we consider the systems which are conjugated, in conjugated system we get the concept of resonance, and when we get the concept of resonance, then we get the concept of resonance hybrid, right? So the resonance hybrid, or the real structure, so it cannot be drawn on paper. The resonance hybrid contains some abnormal electrons because the electrons are not fixed, and the lone pairs have some bonding characteristics as well. So the lone pair on oxygen, right, in case if the resonance is occurring, if the resonance hybrid is appearing, then that lone pair is also showing some bonding properties as well. So it's not only fixed on the oxygen atom, right, but it's also visiting some other atoms as well. And the bond pair, they are moving between different pair of atoms as well, right? So it means that whenever we have a conjugated system, then we'll have resonance. Whenever we'll have resonance, we'll not be able to describe the actual structure of resonance, actual structure of the molecule, and the actual structure is known as resonance hybrid. And whenever there's some resonance here, it means electrons are not normal, right? So what do we mean by normal electrons? Normal electrons are localized. So whenever we have delocalization, whenever we have resonance hybrid or resonance, then we have some abnormal electrons. Why they're abnormal? Because they are not fixed. right? The lone pair is not fixed or is not close to only one atom, but it also showing some bonding properties, right? Also, the bonding electron pair, it's not fixed between two atoms, also moving between different pair of atoms as well, right? So these electrons step outside the boundaries which Lewis theory has set for them, right? So Lewis theory that says that all electrons should be localized, but here in the conjugated system we see the electrons are being delocalized, right? So this delocalization is outside Lewis theory, and that violates the Lewis theory. Alright, so when we are seeing some resonance structures, I already mentioned that resonance structures are represented by that arrow, and that arrow shows that both of these structures are not real, but they are contributing some real structure, and which we cannot draw here. So if this is a big partial representation of this real structure, here we are showing that electronic density between this oxygen and this oxygen is equal. So there's double bond between these two and double bond between these two, but the problem is there, if we draw the double bonds here, then oxygen will have 4 bonds, which is not possible, right? We cannot draw 4 bonds for oxygen, so instead we say that this actual molecule is shown in terms of these 2 molecules. So these 2 molecules together explain the structure of this original molecule. So this is known as the resonance, right? So if you see that this oxygen has positive charge, and this molecule is partial negative, and in the contributing structure we have a positive charge on oxygen, negative oxygen here, and then we have positive atom and negative oxygen here, right? So when we have to spot the delocalized electron, if you're wanting to study that which of the electrons are delocalized, right, in the place, then the easiest way is to compare the electrons in resonance forms, right? So just forget the structure, just see the resonance forms. So these are 2 resonance forms, right? So in these 2 resonance forms, if pair of electron remains same, it means that's localized, right? So you can see that this lone pair remain fixed on the oxygen. It means this lone pair is not delocalized. This is localized electron pair. Similarly, this positive charge remain fixed on both the cases. It means this positive charge is also localized, right? And if you want to see the delocalized, just say, okay, this pi bond is here, but in the other structure this has moved here. So this pi bond, right, this pi bond is delocalized. Similarly, if you see the lone pair of electron, right, so if you see that here we have, okay, 3 lone pairs, here we have 2 lone pairs in the structure, we have here 2 lone pairs and 3 lone pairs. It means one of the lone pair is delocalized and one of this pi bond is delocalized, right? So just by seeing the structures, just see that which of the bonds or which of the electrons are becoming different in all of the resonance structures, right? So atoms or the lone pairs or the charges that remain same, it means they are localized, and this position is becoming different, then they will be delocalized, right? So from the structures from above, both structures, you are seeing the delocalized and localized electrons. So you have to find that which type of electron pairs are delocalized in each structure, right? The answer I've already told you, but that's just to show, to let you know that how can you determine the structures, right? So again, continuing with the localized and delocalized bonding. So localized electrons that are not fixed between atoms. So this delocalized label also applies to bond and charges. So bond can be delocalized, a charge can be delocalized. So a delocalized bond is a bond that appears in some resonance forms but not in the other. Similarly, delocalized charge is a formal charge. Right, so we have discussed about the formal charge in detail in this lecture earlier. So delocalized charge is a formal charge that appears on one atom in resonance forms and not in the others. So if you just see the previous slide here, you can see this bond, okay, which is different in one structure and it's not present here, right? So it means this bond is delocalized. Similarly, this charge is present here in this structure, but in this structure this is not present, right? It means this charge, this formal charge, is also delocalized, right? So electrons can be delocalized, a bond can be delocalized, and a charge can also be delocalized. So that's the end of lecture. I hope that you have understood about the concept of resonance, the resonance structures, the formal charge, and what do we mean by the localized and delocalized bonding. And also I hope that you have studied and your concept about the delocalized bonding is clear. The delocalized bonding involves the delocalization of electron, it also involves the delocalization of a bond, and it also involves the delocalization of charges. That's all for today. Thank you.